Okay, so we're going to start looking at various different sort of processes that allow us to solve problems. And I hinted at right back at the beginning of the very first video in this topic, the idea that different problems, be it you're trying to visit all the nodes, or you're trying to travel all the edges, or you're trying to connect everything in the cheapest way. There's lots of different processes. So what we're going to look at for the rest of this chapter is finding what we call the minimum spanning tree. So a tree is where we have connected all the nodes with edges in such a way that there are no cycles. So there's no way. So the diagram I'm showing you here, there's loads of cycles in this one because you can go from A to F to B back to A. Okay, so there's a cycle here. Okay, there's a cycle here, A, B, F, and E. There's a cycle. There's loads of cycles there. Okay, so how could I connect up A, B, C, D, E, and F in such a way that there are no cycles, but they're connected in the cheapest way possible? Okay, so you can see there's weights or values for each of the edges. So ideally, I want to pick the cheaper the edges with a smaller weight, and it's not a case of trying to make an efficient network that allows us to travel between any of the nodes to any other node as efficiently as possible. All I want to do is make sure they are connected into a single graph some way. Okay, it doesn't matter how long it might take you to get from F to C, but the point is that I've just been able to connect them. Classic example here is when you're connecting up communication systems, which are, in terms of traveling along those networks, is extremely quick. So how long it takes to get from one place to another is not important. It's just the fact that of trying to get each of the nodes connected somehow. So a minimum spanning tree, shortened to MST, is this idea of a network. It's like a subgraph. So what you see here, I've got a graph here, but I'm now going to find a subgraph that connects those 6 nodes in such a way that the weight is minimized. So there are 2 algorithms. So an algorithm is the name given to this idea of a process, a structured, systematic process where you follow a set of steps. Sometimes you might feel as though it is frustrating because it feels like, sure, I can see that the answer is. But just to say, you're going to have to be patient and just work through in a systematic way, following the algorithm correctly. And you're going to have to make sure you show that you're doing that, okay, for examination purposes, I suppose. And there are huge connections here with computer programming. And the idea is that you would program a computer to follow a process. Okay, if it does this, do this. If it's that, do something else. So you're practicing a process that a computer would do the hard work for you. With simpler networks, you should be able to do it yourself. You'll come to a point where you feel as though, jeepers, that network is far too complicated. It'd be easier for me to spend my time programming a computer or using a program that's been made and actually getting the computer to do it instead. So there's an element of that going on. There are 2 different algorithms, and for the second one, the prims, we're going to look at a sort of a third method, an extra way of doing prims. 2 different ways of doing prims. But I'll go through Kruskal. So Kruskal is fairly straightforward in that we are literally going to pick off edge by edge the cheapest edges. Okay, so you're trying to find the arcs with the smallest, the least weights. Now again, you're probably looking at this right now whilst I'm jabbering on, and you're seeing which ones are the cheapest ones, and you probably pretty much know you can pick fairly quickly, and just because you're intelligent, you better do it fairly systematically, but also quite quickly. But I'm again, I'm going to say to you, there is an element of you having to take your time with this and make sure it is completely systematic. And in essence, there's some checks and balances in there as well. So I'm going to take you through that process. And the key thing here is that we just get ourselves organized. So if I look at this network, I can see there's various different values, 8, 6, 7, 9, they're single digits. Then we've got 12, 11, 13, 14, which are double digits. So I suppose something that we can concentrate on, there's a 10. We can concentrate on the single digit ones at the moment, and the smallest one is the 6. So what I'm going to do is I list out, okay, all of the edges. So EF has a weight of 6. Then I've got AF, which is a weight of 7. I've got BC, which is a weight of 8. I've got BF, which is a weight of 9. You can see what I mean by the fact that you're probably sitting there going, oh, geez, why does he need to list them all out? Okay, but there's BE, which is 10. BD, which is 11. Now, so I've gone through these 6, 7, 8, 9, 10, 11, 12. They're very helpfully, actually, this particular question, they're all unique lengths, okay, and it's actually quite easy to see that they've just literally deliberately created a series of arcs which are all unique lengths. So 6, 7, 8, 9, 10, 11, 12, 13, 14. So I've listed them out, okay, and so now what I'm going to do is I'm going to take one at a time. Okay, I'm going to take the cheapest one, okay, and find that. So that's from E to F. Actually, do you know what? I'll use a different color, slightly different color. That's not much different, is it? Let's go with the yellow. Oh, that's even worse. Well, I couldn't plan this in advance. Right, okay, there's E to F. And we're going to actually just color in E to F. So E and F are now in this spanning tree. Okay, and A, B, C, and D are yet to be connected. Okay, so we've got E, F. Now, AF is of length 7, and straight away, one thing I'm doing in my head, and I'll verbalize it, I'm always making sure that I'm not going to create a cycle. It's really important you understand you cannot select it if it's going to create a cycle. The argument actually is that, you know, if you select an edge that creates a cycle, you didn't need to select the edge because the nodes are already connected. We're trying to connect the nodes. So BC is a length of 8, and that connects up B and C. Now, what it doesn't do is doesn't connect up, B and C is not connected up with the AF and E yet, okay? Bear with us, okay? But we're getting our way through the various different nodes, slowly but surely. Then BF is a length of 9. So does that make a cycle? If I were to select that one, no, it wouldn't. And it now connects up BC with the AFE. So that's very handy. And then BE. Now, if I select BE, which is length of 10, that will create a cycle. You can see that if I connect up that one there, it's now created a cycle. BEF is now a cycle. I didn't need to select BE because B and E were both so far already selected. So taking the edge BE is of no benefit to me. So we're not going to do BE. Then BD. So BD, now D hasn't been selected yet, okay? So this is useful. So BD of length 11. And then everything else is going to be a waste of time because I've now got A, B, C, D, E, F. They are all connected, okay? And anything else will create a cycle. So CD will create a cycle, D, E, they'll all create a cycle. So that is my sort of finished minimum spanning tree. And if we were to just add up the cost, so 6 and 7, 8, 9 and 11, 20, 35, 41, I think. So 13, 22, 33, sorry, 13, 21, 32, 41, yeah. So 41 is the cost or value or the weight of this particular minimum spanning tree. Now, a couple of things. Sometimes you can have more than one spanning tree that is considered to be a minimum spanning tree. Sometimes you can have a network where there are several different minimum spanning trees. They are both equally short. Okay. Other thing to be aware of is, now here in this question there were 6 nodes, and you'll see that there are 5 arcs that I've connected up. So if for whatever network you have, if there are n nodes, they're going to be n-1 edges. So effectively, once you've done your order, you're just finding one less than the number of nodes there are in terms of arcs, and then the final step is to add up the cost. So I suppose there are n processes in total, n-1 edges to find, and then finally the total weight. Another example, just to make the point, we have a network of a series of places, and the idea is you want to connect up these housing estates with cabling, and again it's fiber optics. It doesn't matter, how Abbey is connected to a fir tree, and the shortest distance between the two is of no importance. All we want to make sure is just each of these nodes are connected. Now there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There seems to be 10 nodes, so I'm going to have to make sure I have 9 arcs. I need to list out the costs of them. And this is the boring bit. This is the hassle, trying to actually find all the shortest arcs. So from island to harbour, we've got 3.2. From harbour to Glenside, we've got 3.3. We've got Bayview Cloisters, which is 3.4. We have Glenside to Fir Tree, which is 4.8. We have Cloisters to Island, which is 4.9. We have Domain to Egret, which is 5.0. I've always wondered about the name Demesne. I'm told it's Domain. Carrying on, I digress. Abbey to Bayview is 5.1. Egret to Fir Tree is 5.2. Now I'm beginning to, my head's beginning to hurt now, trying to make sure I'm actually getting everything. So Abbey to Cloisters, 5.6. Of course, the question, that the difficulty with this process is, are you sure that you've actually listed all of them so far? So I'm working the way through this, but there's always a possibility that I've missed something off, and you're always going to make sure that when you go through this list, you can always add one in if you realize you've missed one out, but just be aware that once you've done your list, you should double check that you've actually got all the arcs. It's not an easy process. Okay, so anyway, 5.6 Abbey to Cloisters. Then I'm looking for any more 5s. There are none. Going to the 6s, then I've got Egret to Harbour, which is 6.1. I've got Cloisters Domain, which is 6.5. Cloisters to Johnstown, which is 6.7. And Domain to Glenside, which is 6.9. I'll run out of space in a minute. I've got Cloisters to Harbour, which is 7.1. Johnstown to Ireland, which is 7.2. And Domain to Ireland, which is 7.8. Now, so as I said to you, before I go any further, how many of them are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. 1, 2, 3, 4, 9, 10, 11, 12, 13, 15, 16. It says 16 in that list. And then it's a case of just double checking. Do I have 16 in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's 16 numbers there I've counted. There's 16 I've listed the side there. So I'm happy that I've actually listed all of the edges that are relevant. And by the way, there's none that are free. There's no edges that are free. If you find that there's an edge that doesn't have a number on it, by the way, you can sort of list it as being a cost of 0. I mean, that's you can list that first, okay. And the other thing to say is that for example, the 7.1 and 7.8 that you see here, and they cross over. Okay, it's not that this edge is free and this bit here is free. That entirely from Cloisters to Harbour is 7.1, from Domain to Ireland is 7.8, and you can't sort of somehow connect in between and go sideways at that point in time. It's just like it's like a flyover. Okay, so in the last example, I used like a highlighter pen and I just highlighted over the top of the edges that I was selecting. And to be honest with you, that's a very efficient way of doing it. What I'm going to do deliberately here, I'm going to sort of effectively recreate the map underneath. Okay, so I'm going to try as best as possible position the places as you see them on the page here. So working from Kruskal's starts with the cheapest cost. So Island to Harbour of 3.2. So there's Ireland. There is Harbour, and I'm going to connect them up. You might feel as though you want to, I mean, I could actually, I tell you what I might do is I might deliberately just create all the relevant points. There's C, there's A, there's B, there's D, G, F, and E. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We said there were 10, and now I've got them there. So AH of 5.2. Okay, so we've got that. That's a cost. Sorry, 3.2. Then next one, HG of 3.3. So H and G 3.3, and we can include that in our list. Now BC of 3.4, and we can add that to our list. Then GF 4.8, so G to F, that's not going to make a cycle. That's great. I'll pick that one. That's 4.8. C to I of 4.9. C to I, oh, different color. I'll try and keep this the same. C to I, 4.9. Now, DE of 5. So DE of 5, yeah, that works. That doesn't create a cycle. AB 5.1, yeah. EF of 5.2. Now, starting to connect this up now. That works, doesn't make a cycle. Now, AC 5.6. Now, if I select AC, that's going to create a cycle. So I don't want that. That's not going to be viable for me, and I'm not going to include that one. Okay, so actually we can sort of cross it off as such, I suppose, or just, I tell you what we'll do. We won't obliterate the number. We'll put a cross against it. EH, So EH, again, that's going to create a cycle if I draw that line across, so that's of no use to me. CD, again, that's going to create a cycle, so I don't want that. The only one I'm wanting to connect up is J. Okay, everything else is connected up so far. So hang on, CJ 6.7. So that will work. That will create my final arc. I don't need any more. Just as a reminder, there was 10 nodes. I need 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 arcs. I have my 9 arcs. Connecting up my minimum spanning tree, connecting up all the nodes as cheaply as possible, and the cost. So I just have to sit here now and work out what 3.2, 3.3, 3.4, 4.8, 4.9, 5.0, 5.1, 5.2, and the 6.7. 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. And according to my calculator, that works out as 41.6 as a weight, as a cost. So I've sort of modeled a few different ways of doing it in terms of, like, it's quite nice to actually see the tree like that. In the previous example, if I scroll back up, you don't really see the tree. It's actually still, there's an awful lot of the original network there. You sort of can't really see the tree. So to some extent, actually plotting out the nodes and connect them up as separate to your diagram is actually quite it feels more satisfying. You actually see what the tree actually is then. So you should be able to have a go at the exercise that's connected to this. Exercise 11.6, page 224. You should just basically just work your way systematically through it. And obviously, since the diagram is in your book, unless you want to draw all over your book, arguably, you need to take a copy and actually, you plot out the nodes A, B, C, D, E, and actually draw out, as I've just demonstrated to you for this second example. Have a go at that exercise. Any problems, get back to me, obviously. And then what we'll do next is I will show you an alternative algorithm for being able to go through this process.